All right, how's it going, everybody? Welcome here to week 4. Today we're going to talk we're going to introduce our probability chapter here today. Um, we're going to talk about computing a bunch of probabilities associated with random events. We're going to look at some probabilities of some sort of simple scenarios, rolling some dice, drawing marbles from a bag, pulling some cards from a deck. And these are all intended to sort of highlight a bunch of our important probability topics that we're going to need to understand so that we can compute a bunch of slightly more complicated and more relevant probabilities in our upcoming chapters up here. So this is really, in a sense, like our third of three different units in which we are sort of building the tools that we need so that we can put all these tools together starting in unit 4 for, in a sense, the true purpose of this class to actually compute probabilities to make scientific decisions. So a lot of the things that we're building here, we're sort of we're in a sense beginning to wrap up all of our introductory material here to get to truly the goal of this class to make statistical decisions based on computed probabilities. So let's go ahead and get started. So the first thing I want to do before we actually get to any of our probability computations for the day is talk briefly about the law of large numbers. It's something the book talks about, and I feel like this is one of those things that just didn't. I guess it's a wordy enough phrase thing that I remember first learning about this and, in a sense, disregarding it because it was just a wordy long sentence. So I kind of want to highlight an example of what we mean when we talk about what the law of large numbers actually does for us. The purpose of the law of large numbers is for us to make a relationship between experimental results and theoretical results. So what I mean by that is the difference between what did you see when you did the experiment versus what did you expect to see based on what you think that you know about probability. So our examples in this case would be if you're flipping a coin a bunch of times, what you know to expect is 50% heads and 50% tails. However, what you also know could certainly happen is it's totally possible that you're going to flip a coin 10 times and get 8 heads and 2 tails. That's really honestly not that weird, even though 80% and 20% are very far off from our expected, our theoretical probabilities of 50-50. What we expect to see happen, the large numbers part of the law of large numbers says, the more trials that we do, the larger and larger our sample size gets. We expect our experimental results to get closer and closer and closer to the theoretical results. This sort of says to me, on the small scale, anything can happen. When you're flipping a coin just a couple times, if I flipped a coin 4 times, it's not really that weird at all for me to just get 4 heads, right? Even though we know that maybe the most likely outcome is 2 heads and 2 tails for flipping a coin 4 times, none of us would have our minds blown if we just got heads 4 times in a row. So the law of large numbers says on the small scale, if you only have a small sample size of like 4, then we don't necessarily expect our results to match the theoretical results because on the small scale, things can deviate. But together, when you get together a large group of results and you average them, we certainly expect as the group gets larger and larger that their overall result tends more and more towards the theoretical results of 50% heads, 50% tails. I guess my opposite example, my non-example here would be, while it is not strange to flip a coin 4 times and get 4 heads, it would be incredibly strange to flip a coin 40 times and get 40 heads. That would be wild and borderline unbelievable right there. So the more and more trials you do, the more and more you expect the average of your experimental results to become closer and closer to our theoretical probabilities, our expected results based on what we believe that we know. So let's real quick watch some program do a little bit of this for us. So if I switch over here, all right, still got audio. And we've seen a little bit of something that looks like this before already. Again, you guys aren't writing any code this semester, but I certainly expect that you can, do your basics of reading this stuff right here. So I'll just briefly walk you through the couple lines of code we're looking at. The first line here is just going to bring in a library called NumPy. It's a library that has a bunch of probability and statistical and numerical computations built in for us right here. So this just says, hey, NumPy library, be known so that I can use some of your functions here. What I'm going to do here is I'm going to start by flipping only 10 coins. So I'm going to make a variable called n because I think of n as my sample size, and I would like to flip 10 coins and see what my results are. So I'm going to say, hey, NumPy library, from all of your functions based on randomness, use the random integer function and select random integers where there are two choices of integer. It by default will start these choices at 0. So if you have two choices starting at 0, those choices are 0 and 1. How many of them do we want to do? Well, do a sample size of n, and we've decided that n should be 10. So what this should do for us is this should determine 10 random numbers that are all going to take on a value of 0 or 1, the first two integers. We can choose to interpret 0 and 1 as heads or tails. It honestly doesn't even matter which one we consider to be which one here. But the point is, X will now be a list of the zeros and ones that have been randomly selected. So let's go ahead and actually see the list in this case right here. So I can say, hey, know the library. Then I can say let n be 10 and therefore do 10 flips of a coin and get the results. So we can see here, here's our 10 results right here. And again, we can interpret like something like zeros as heads, ones as tails, or vice versa. It doesn't matter. Each of these are in a sense equivalent to each other because they both have a 50-50 chance. If I then want to know what was my average associated with this, and again, if one is heads, then maybe we're looking for the average number of heads. Well, it looks like what I can do is I can actually just add up the numbers in this list right here, and that will tell me exactly how many heads that we have, because 0 is tails. That's the things that wouldn't, in a sense, get accumulated in the sum. So if we add up the number of heads and divide by the total number of observations that we had, then this will tell us the average that we saw. Now, I do have to say real quick, you should see a ridiculous number down there, considering this should have been probabilities out of 10. Hopefully you're seeing that for the 0.7 that it is. It actually turns out that computers have a hard time with numbers being in things like base 10 because computers think in base 2 in binary. And so it actually turns out that there are some pretty simple numbers like 0.7 that are incredibly difficult for computers to actually know the number exactly 0.7 right there. What application is this through? Good question. So what I'm writing this code in right now, this is the programming language Python, and the application that I'm using to write it is called Jupyter Lab. I don't know if you can see that right there, but Jupyter Notebook and Jupyter Lab are. Jupyter Notebook was the original project, and then when they decided they wanted to make some more forward future changes, they kind of revamped the project into being Jupyter Lab. But the very cool thing about Jupyter Notebook and Jupyter Lab is that you can write, okay, I don't have any other ones selected right here, but it turns out regardless of what programming language you like to use, Jupyter Notebook, Jupyter Lab support over like 300 different programming languages that you can write in this sort of cell style thing. So this is nice for data science and explorative type things where you might want to compute a result, think about it, graph it, based on the results in the graphs, do some more code down below. So it kind of allows you more of like a thought process rather than trying to draft one document that what does one task. So this Jupyter Lab setup is something that I really like with this sort of cell-based interaction right here. And it works with almost every programming language, which is very cool. So so here I'm computing this average, and again, don't worry about that number being kind of stupid right there. We should be interpreting this as 0.7, which it is insanely close to right there. And so all this is really telling me is 70% of these 10 flips came out heads. Now what we know is that coins are not 70-30 split between what they land on. It should be 50-50, but this was a small number. This was not a large number as the law of large numbers proposed to us that we need so that we can see these get closer and closer to their theoretical. Now notice in this case I flipped 10 coins and I did in fact get 5 heads, 5 tails right here. This obviously can happen. This is our most likely thing to happen, but again, I can keep on redoing this. So 40% heads, 60% heads, 60% heads, 40% heads, 60% heads. And we see that we keep on getting results that are maybe near, but here we go again, only 30% heads in this case. But again, that's not that strange because we only did 10 as our sample size. Now, the thing that you have to ask yourself is, if I flipped a coin 1,000 times, would I ever expect to only get 300 heads and 700 tails? And the answer is no, that's insane. That would be a wildly unlikely outcome here. So if I bump this up to 100, we can still see, it's a little strangely formatted there, but 100 zeros and ones. And I can go ahead and compute this here. And notice here 53%. It's a little bit closer to 50% than some of those 40s and 60s that we were seeing before. And so again, we can run this a bunch of times, and the numbers that I'm seeing down there are all decimals that are a good bit closer to the 50%. I mean, I really don't expect to see anything wider than 40% to 60%, knowing that our theoretical response here should be 50% in each case. So now what I'm going to do is I'm going to bump it way up, and let's flip 10,000 coins and see what kind of result we're going to get. I'm no longer going to output the ones and zeros here because I don't want to output 10,000 ones and zeros, but we're still going to be able to add up how many heads, divide by the total number of flips. And what we're going to see now is, okay, 49.8% were heads. 49.5% were heads, right? And so now what we see is, because now that we're flipping a very large number of coins, we are seeing our experimental results be very, very close to the anticipated theoretical distribution of 50%. When we had small numbers, our experimental results deviated wildly from our expectations. When we have a large number of samples, our experimental results often very closely match our theoretical results. So one of the really nice things here is that there are lots of things in the world that are very meaningful for us to compute a probability for, but for which there is no direct way to actually predict the probability. So all we can do then is do thousands or millions or billions of trials, see what type of results we're getting, and say that must be what we should expect to always see in the long run then. So sometimes we run simulations to determine probabilities for things. Other times we can compute them directly. Most of this section is about directly computing probabilities rather than performing simulations. But one of the things that I've personally been interested in the last couple of years is saying types of events where it's incredibly hard for us to come up with legitimate probability statements to compute the probability, but maybe we can just perform an experiment lots of times. There's one of the ones that I've been working on for a while, math problem that I've come across, where I do know that it's possible to come up with an actual expression for the exact probability, but it is beyond me to create it. I have written a pretty extensive program to simulate it, and I've just been trying to get to the right answer by simulating it lots of times. But it turns out in the particular problem that I've been looking at, I have run over 400 million trials, and I still haven't gotten my probability to stop sort of changing numbers. My long-term experimental results are still wobbling even at the first decimal place for as far as the percentage of successes in a sense goes right there. So in some cases, even running an incredibly large number of trials still will have some variability in the results that you're going to see out there. But again, the law of large numbers is just trying to get the point across that the more trials you do, the more we can expect our experimental results, what we got in our experiment, to match the theoretical results, what we predict would happen in a pure probability sense. Okay, so there, I think I've run enough example code right there. We'll do one more time, see if these numbers keep being really close to that 50% because we have a large number of trials. Now, it's certainly the case that any reasonable person should be sitting here saying to me, well, how much is large? How many trials do I need to do before I can really expect that to happen there? And the answer is it very much depends on the scenario. We're going to look at a few contexts later this semester where we're going to ballpark some numbers where we say this sample size is probably good enough. But then later we'll see different scenarios in which we'll identify that because there are some differences in the way that we report our answers, there will be differences in the expected number of trials that we need to see our experimental results approach the theoretical results. So this is one of those things where it doesn't say the law of sample size 200 for a reason, and that's because this is vague on purpose. How large is large? Well, the larger you get, the closer it gets. This isn't a thing about saying once you're this large, then you're close enough. It's not one of those things. So there's my law of large number statements. I always just feel obligated to kind of show a little example of that in action. As your sample size grows, experimental results should approach your theoretical results. Okay, so let's actually look at working through some of our examples here today. We want to identify some quantities of interest, evaluate some probabilities. We're going to compute a lot of fractional results here today. If you guys have seen in the quiz that I posted just yesterday in Canvas, so probably not many of you, that the quiz is going to have you, I asked for almost every single one of your answers as an unreduced fraction. Lucky for you guys, we don't need to be messing with our fractions a lot. A lot of the times it's easiest to read our answers just as a raw fraction without any reduction or converting to a decimal or percent. So I'll leave a lot of my answers like that here today. First things first, we're looking at identifying a couple kind of more basic vocab words right here and a couple pieces of notation. So in example one here, we're going to roll a 20-sided die. So a 20-sided die has values of 1 through 20 as the possible outputs on the die. And we are interested in identifying the following three events. We'll call these events A, B, and C. Rolling an even number, a number divisible by 5, and a number less than 8. Those are our three special events of interest for some particular purpose. So in general, let's just identify a couple of our basics here. When we talk about, and actually, I'm trying to do myself a favor here and keep some more information on screen for us, so I feel better about scrolling away. So here's the things we want to identify. Here's all of this example one information right here that we're going to use to help identify it. So first things first, a sample space is just the set of all possible outcomes. When I'm rolling a 20-sided die, all of the possible outcomes are the 20 different things that I could roll on that die. So I can identify our sample space here as the numbers that are going to be on that die, 1 through 20. There are 20 things in the sample space here. So I think maybe another thing that is worth saying here is n equals 20. My sample size is 20. The sample space is the space of all possible results that we could end up seeing out there. I can also discuss event space. An event space is all possible results associated with a particular event. We see that event A is roll an even number, so it should just be associated with just the evens. So there is my event space for event A. My event space for B, B was a number divisible by 5, so 5, 10, 15, and 20. Those are it. So these event spaces are always a subset of the sample space. So the sample space has everything in it. So it has to be that we're just picking out of the sample space to identify each of these guys here. And so these are all subsets of the sample space. It could be a full proper subset of the sample space. It could be the entire thing. Maybe my event is just I roll a whole number. Well, technically, all the numbers in the sample space are whole numbers, so that event would be the same as the entire sample space. If we want to talk about probabilities now, this is certainly a thing of interest here. So in general, probability statements are always notated this way. Capital P indicating compute the probability of, and the event or events always go inside. I do want to say, by the way, you are welcome to get as like wordy or verbal with this as you want. Since A was our roll and even number, it's totally okay if you want to write things like this. This is perfectly good math notation right there. What is the probability that we roll an even number? The capital P indicates we want to compute a probability. What goes inside the parentheses is a descriptor of the event. It's very often nice to give names to your events like A, B, and C, or even could have been a name of an event or something like that, as long as it makes sense, just to give you the opportunity to use some shorthand. But if you want to literally write a whole phrase in here, that's not weird at all. That's a very typical thing for people to do. So feel comfortable with your notation there. So if we want to compute the probability of event A, what we want to compute is out of all of the possible outcomes, which of the outcomes are associated with event A? In general, this is typically denoted as successes over trials. But in this case, we don't really typically have maybe I should say, just n right there. It's really the size of the sample space that we have to work out of. In this case, we consider our successes to be anything that falls in the A category. That would be a success, getting an even. What we can see here is that there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 things in the even category, which makes sense. It's every other value here. So it looks like this is going to be a 10 over 20 for our probability here. 10 out of the 20 items on the die face are what we would consider a success here, and even. We could certainly reduce this down to 1 over 2. We could certainly call this the decimal 0.5. We could certainly call this the percentage 50%. So all of those, I would say, are good answers right there. To be perfectly honest, I kind of feel like out of those four different ways to report an answer, I would have to say that 1 over 2 is maybe my least favorite of all of them. I feel like I get the same information out of 1 over 2 as I do from zero point 0.5 and 50% because that it does turn into a nice clean decimal and percentage. But I feel like 1 over 2, in a sense, we've lost the information that there were 20 total possible outcomes and 10 of them were associated with our event of interest. So in a sense, this 10 out of 20 here, since that's an easy fraction for me to understand, I like that because it's still maintaining sort of the raw original data, whereas any simplification of that fraction, you're losing the true numbers of which we were actually counting out of. So really like I really do like in probability senses, unless our numbers get huge and annoying to kind of imagine in our heads, 10 out of 20 is not a difficult fraction for me to think about. I like that one in that unreduced form right there. So let's look at some of our other things, and I want to introduce a little bit more notation here. Oh, by the way, one other thing I want to talk about, and that's this word right here. This is one of those words, successes, that I want you guys to really understand that successes is very much being used in a statistical sense, not in a like regular life sense. What I mean by that is if we are a researcher trying to determine if, for example, being exposed to, if you have a lot of lead in your water, are you going to experience higher rates of blood cancer maybe? Well, in that case, the statistical researcher that's doing that research would be sampling people to see if they have developed that blood cancer. And if he finds that somebody does in fact have that blood cancer, that would, in a statistical sense, be counted as a success because we did see the thing of interest. Obviously, having cancer is not a success, but in a statistical sense, we define a success to just be any sort of a positive result in that you tested positive, right? You test positive for cancer, obviously it's a negative thing. You test positive, you have it, right? So just realize there that success is very much a statistically defined word, not a like, did you get the result you wanted? Well, no, it's just did you have the thing that was being tested for, yes or no? So just as our definition of success there. So other things here, we want to help define our and our or words. And what you can see is that I'm using different notation for these two guys right here. This notation right here, I remember that that downward facing U shape is the word that is associated with, or is the symbol associated with and, because that symbol to me looks like an N. That looks to me like and I say that N for an extra four N's right there. And it looks like an N. This guy right here is referred to as a union of B and C, as we'll see in a second, and therefore it's pretty easy to remember that union starts with a U, and we use a U shape to join those guys together. So if I am interested in the events of A and B, this would also be verbalized. Maybe I'll step out of this. This is A intersect B, or a union, A and B, and I'm going to do this. So that's how I remember it, is that N and right there, as far as that symbol goes. And this is just the collection of all objects that are both in A and in B in their respective event spaces. So this is saying, in a sense, what are all of the ways that I could both achieve event A and event B? I need to both roll an even number and roll a number that's divisible by 5. So looking at my event spaces over here, I can see that 5, so by the way, I typically start with my smaller event space and see if it's also in the larger. 5 is in B, but it's not in A. 10 is in B and 10 is in A, so it looks like 10 is in both. It's both even and divisible by 5. 15 is divisible by 5, but it's not even, so that's not in there. But 20 is both even and divisible by 5. So it looks like there are two objects that are in the set A intersect B, or that are both in A and in B. And we use this symbol right here to indicate the intersection symbol. What is the intersection of these two sets to determine that? Very similarly, our other kind of partner of the intersection is the union. This is a union. Oh my gosh. And I am going to do a similar thing here, underline, bold, a union B, and we use that U-shaped symbol to suggest this. When we're talking about the union of two sets, we're saying collect them all together. It's sort of like saying we have two objects or two bags full of objects. Dump both of those bags together in one giant bag. What's in that giant bag now? Now, the important thing to identify about our union stuff here is that when we're talking about sets, we never really have repeats here. So this is just saying, tell me the set of all objects that are either in B or in C or in both. It's acceptable to be in both here. This or is not an exclusive or. It doesn't just have to be in only one or the other. It could be in both. So in this case here, that means I'm going to get everything that's in A. I'm going to get everything that's in B, and I just don't want to include any doubles. So it looks like 2 is in B, 2 is in A. Oh, wait, oh, sorry. We're doing B and C. Oh, I've been talking A and B. Okay, we're looking at B and C here for this one. Sorry. Now I'm going to take my breath and actually say this properly. B or C. I want the list of all objects that are either in B or in C or in both. I'm going to try and list them in order here as I see them. 1, 2, 3, 4, 5, 6, and 7, because all of those are in C. There are also the values of 10, 15, and 20. You should notice here that 5 is in both sets, so it is included. I didn't list 5 twice because there's not two different 5s that I can roll, right? 5 is one of the objects that is in both. So what I kind of want to highlight right now is that what we really just did is we came up with a list that is representative of a Venn diagram. If we're looking at a Venn diagram here, then you should notice that for, and I'll do this for A and for B, and then for B and for C. If we're looking at the A and B, sorry, let me just go back and make this actually big enough that we can actually see it here. Trying to get some actual overlap space here. So if this is our A and our B Venn diagram, then what you should notice is that A has all of our evens, B has all of our divisible by 5, A and B is what's in the middle. So this 10 and 20 falls into both. But 2, 4, 6, 8, 12, 14, 16, 18, those fall only into the A part of the Venn diagram. 10 and 20 certainly belong in circle A, but they also belong in circle B. So 5 and 15 are over here. So you should notice that this is the and parts in the middle. The and happens where the intersection is between A and B. On the other hand, we could draw our Venn diagram for B and C here as well. And for B and for C, gosh, I'm not even going to be able to get them all in here. You should notice that, let's see here, for B, what's the stuff that's in B? That's going to be 5, because 5 is also in C, but 10, 15, and 20 are all only members of B. On the other hand, C has 1, 2, 3, 4, 5 is already accounted for, 6, 7. That's in it right there. So here you should notice that the union is the whole thing. Union is everything that's represented in here. The intersection is what would overlap between the two Venn diagrams right here. It's just in the shared part of the Venn diagram. So I do think it's really useful to picture pictures that are associated with these. We can draw a diagram to think about any of these and or statements, any of our unions and any of our intersections. So we can keep going here. A and B and C. So what is the set of the stuff that is in all three of these guys right here? Well, this is asking me the question, what's in all three? So I think it'll actually be helpful for me to scroll up and look in them here. So I'm seeing 1 is not in all three. 2 isn't in all three. What might even be in all three? 5, no. Let's see. 10 is not in all three. So this one only has numbers 1 through 7. The only number it has in common with this set at all is 5, and 5 is not in A. So it doesn't look like there is anything that is going to be in this set right here. So I actually need a new symbol. Let me bring this down real quick here. Stay there. Now, I'm sure it's got this symbol for me here. There it is. This symbol right here is called the empty set or the null set right there. So this is my way of indicating a set that has nothing in it right there. It's sort of like a 0 but with a dash through it. The null set or the empty set. Right? This is just my way of saying there is nothing that satisfies this intersection right here. If we were to make a Venn diagram of these three circles overlapping, there would be nothing in that centermost part that's shared by all three. There is nothing there. Now, on the other hand, we could say what is collectively in all of A, B, C? Where is the give me all the objects that are at least in one of the three of the sets. So is A or B or C says an object can be just in A, it can be just in B, it can be just in C, it can be both in A and B, it can be both in B and C, it can be both in A and C, or it could be in all three A, B, and C. As long as it's in at least one of them, you're in. So this should be most of the stuff I'm expecting here. So let's see what we got. In this case right here, I'm trying to just do these in order so I stay organized. So one is in there. And in fact, based on set C, I know that I'm going to get 1, 2, 3, 3, oh my gosh, 3, 4, 5, 6, 7. I know those are all in there. 8 is in because it's part of group A. It looks like there's no 9 out there, so we've missed 9. 10 is in there because it's in A and B. And I'm going to do this. Extend this right. Well, no, I think we'll catch on there. We've got no 11. I've got a 12. I've got no 13, but I've got a 14. I've got a 15. I've got a 16. I've got an 18, and I've got a 20 right there. So we can get all the things that are collectively in any of those sets there as well. Other things that are important right here are not events and not probabilities. These are generally referred to as the complement. The complement is something that finishes that grouping. So if I were to say to you, what is so we talk about this, actually the first time that I ever heard the word complement defined mathematically for me, it was in geometry, where we say that two angles are complementary if they add to 90. And so if I were to say to you in trigonometry, what is the complement of a 40-degree angle? You'd say it's a 50-degree angle because in a sense, it is the amount of angle that completes the beginning part. It's what finishes up the getting to that nice whole value with the other one. So the complement here, so we verbalize this as the complement of A. Then it looks like here we are looking for all the stuff that is not in set A right here. So this would be all the odds right here. The complement with an E. Gotcha. Really? I could see that. And yeah, using that upper C is also a typical thing right there to do instead of that prime notation, it's certainly another notation that's out there to do the complement up there, like that guy, I guess, with the complement of it right there. Some way to indicate that it's the other stuff out there, right? In this case, we could say that it's the odds. You don't necessarily normally have a good name right there, but we can look at some of these probabilities as well right there. So you should notice before we computed that the probability of A was 50%. You should also notice here that we're picking up 10 out of 20 objects right there are in not A, are in the complement of A. So it looks like we're again going to get a 10 out of 20 here. And I think a good thing to notice here now is what's going to happen when we talk about the relationship between A and not A. Our first one here is what is the probability that our roll of the die either gives us something that is within set A or something that is not within set A. Well, the whole definition of being a complement is that it is all of the rest of the parts that are out there. And so if we're looking for A or A prime right here, this is saying, what's the event that your number is even or that your number is not even? Well, it should always be the case that that is going to be a 20% right there, right? So a 20 out of 20 or oh my gosh, 20 out of 20 or a 100%. It should always be the case that the probability of an event or its complement occurring should always be 100%. This is just like saying, what's the probability that event occurs or that it doesn't occur? Well, it's a 100% of chance that something is going to happen right there. Conversely, what is the probability that we both roll an even number and a non-even number? Well, that can't happen since these are disjoint from each other. So here we're always going to see if it's a probability of a or not A that we're going to be landing at a 0% as our probability associated with that. That's not particular to this problem. That is just generic to all complementary probabilities. What's the probability that you're both experiencing one output or one event and experiencing not that event? Well, it can't happen that you experience both an event and not that event in one trial. So that will always be a 0% that we're seeing right there. All right, so just to get some of our basic notation and definitions out of the way right here, we can think about rolling that die. We got our complements, we got our unions, we got our intersections, we got some set notation here, null and empty set. So let's look at something that's going to be, oh wait, ooh, we still got a couple more exciting ones right here. We still have some of our conditional probabilities that we want to talk about right here. And we'll actually do these ones a couple different ways. And so let me give myself a little room since I want to compute these each two different ways, and then we'll be done with our die rolling right here. So if I'm looking at the probability of A given B, that's like saying, what is the probability that we roll an even number given that we rolled a number divisible by 5? So what is the probability So that is exactly what I'm asking when I say, what is P given A right there? What is the probability that we roll an even number, event A, given, that's what the vertical bar is indicating to us there, that we rolled a number that is divisible by 5? Well, I'm going to start usually with the fact that we rolled a number by 5, right? So event B here to me, I know what event B is. It's going to be the fact that we got a 5, a 10, a 15, or a 20. The question is, I know that I rolled one of those. Given that I rolled something associated with event B, what is the probability that we rolled an even number? And so it looks to me like there are 2 out of the 4 things here are going to give me the even number out of those guys. And so I'm seeing 2 out of 4, or a 50% chance of probability of A given B. Our other way to do this is actually using that formula right there, that Bayes formula that we're talking about right there. So in general, our formula for this is that A given B is going to be equal to the probability of A and B divided by the probability of our second part right there. This is going to be our probability of B. All right, and so we can do this directly as a computation. Didn't we even do this one up here? Probability of A and B. A and B. What are all the things that are in A and B? We can see here that we previously discussed that there were 2 objects in A and B. So this should be a 2 out of 20 for the top. So I'm going to do it like this. There we go. So this is a 2 out of 20 is the probability that we're experiencing up top. On the bottom, what is the probability of being in group B? Well, it looks like there are 4 things that are in event B. So probability of event B is a 4 out of 20. And this is going to reduce to us as a fraction just 2 over 4 right here. And so we can see that we're getting the exact same result whether we use Bayes' formula or whether we, in a sense, just sort of think about it. But the problem is that the just sort of think about it method like I did right here is not always a great idea. But I do want you to realize that, we're looking at, the formula is good right here and it will always lead you in the right direction. But it's good to realize that you can sort of just stop and think about what are the actual events of interest that are actually happening right there, right? So sometimes it's good for you to just literally list out the things that are happening. When I see things like probability of A bar B right there, A given B, it's helpful for me to like get a whole sentence for that stuff and then use that sentence right there to help me think about the actual outcomes that are associated with what I'm interested in. Alternatively, though, this Bayes formula, probability of A given B, is equal to the probability of A and B divided by the probability of B. That's always our good direct computation to take us home on that one. So let's do one more exact same thing right here, and then we'll move on to our next example right there. So probability of C given A right here. We have identified event C as rolling a number less than 8. So I'm going to say Let me get out of the, there we go. Given that we rolled an even number. So the given is what's coming after the bar. The event of interest is the thing that's before the bar. So I want to know what the probability of event C happening, but I'm restricting it to the only knowing that we've already been guaranteed that event A is the thing that has already happened here. So what is the probability of getting a number less than 8 given that we rolled an even number? Well, again, I can think about what is my even number set right here, and that's going to be my 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. And again, I can then identify for myself what are the numbers that are less than 8 that are going to be in this set right here. There they are. And that's going to allow me to identify that 3 out of 20, or 3 out of 10, excuse me, or a 30% are going to be the values of interest right there. Yeah, Jazz. So basically, all I was so Jazz, the setup for it is sitting right here for the events A, B, and C that we're using. And right now, I'm just trying to answer particularly this question right here. I'm trying to compute just this one that's right here. I do have a whole list of these things that's up here, but I certainly will post this document in our Canvas here also so that you can get a snag of these things sort of as the just to kind of reference some answers right there as well. Totally, yeah. And if I forget to do that, certainly hit me up and I can definitely post this for you here. Yeah. So I'm trying to do, by the way, more of the things like this of having this viewable over here. I feel like I keep scrolling away from things like this. I'm trying to do a better job of like keeping relevant information on screen while we like do some work over here. So I'm going to try and be a little slightly more organized with that stuff there here. So again, we did this one just by thinking and listing things, but listing things could be really exhaustive, right? We could have way too many things to actually account for. Hey, clipping those things also works right there. Thank you, Infinitesimal. So we can also go ahead and use Bayes computation for this as well. So probability, let's do this one here, probability of C given A. We can instead compute this as the probability of C and A divided by the probability of just A, the condition that we experience at the end right there. In this case, we have to ask ourselves, what's the probability that we get both a C and an A? And if I look back up here at my A stuff and my C stuff, I am seeing that 2 and 4 and 6 are the 3 out of 20 quantities that satisfy both A and C. A and C have in common 2, 4, and 6. So it looks like 3 out of 20 things belong here. So I'm going to put this as a 3 over 20. And the probability of A occurring, as we saw, was 10 out of 20. And if we do a little bit of fraction math, the out of 20s, they are cancel, and we are left with 3 out of 10. And that is going to be exactly that same 30% that we got before. So I do want to encourage you guys, when you get to some of these conditional probabilities right here, it's good for you to recognize that you can literally just write it out and see which ones are relevant out of the events associated with event A, which of them, which proportion of them are associated with also with event C. Alternatively, Bayes' rule, which is stated right here, that I'll bold right there, is always going to give us a direct computation for any of our conditional probabilities right there. We can see that they match up. Right? Okay, I think I beat my roll on a 20-sided die all the way down there. So let's look at a couple other examples here in a table and pulling some marbles. This will be quite a bit quicker right here, and we'll be good with our first couple sections here. So example 2 here, we're going to look at drawing some of the similar information out of a table. I'm going to reference both this table on the side so I can scroll away from it as well as right here. So we're going to pull some students. We're going to ask them if they're male or female. We're going to ask them if they're working full-time, part-time, not working at all. Yeah, video game cheer there. I can definitely answer your question at the end here. I'm going to try and get through a lecture video here. What I am interested in determining are a bunch of probabilities associated with the males and females and their work status over here. So the first question that I ask is something that I want to really highlight here because the book does not, and this is really an important thing to me. This is how I manage to compute all of my associated probabilities. What I'm first asking you to do here is to compute a marginal distribution for each of the two genders, and I'm going to kind of label my variables over here. This is the gender variable, and this is the work status variable over here, right? So each of these variables, the gender variable takes on the values male and female. The work status variable takes on the values not working, part-time, and full-time. If I'm going to look at a marginal distribution for work status, then I could make, in a sense, just a little tiny table here. So not working, part-time, and full-time. And I'm just going to make like a one-directional table right here. And what I want to know is, what is the number of people that fall into each of these three categories? The easy way to do this is we just do a little vertical addition right there. 29, looks like here 101, and it looks like here 25. This is my distribution of work status. I can see that there are about 150 students, about 100 of them work part-time, about 25 each don't work or work full-time here as well. So here is my marginal distribution for work status. It's showing me the distribution of responses for just that one variable rather than for both variables combined in a table. Similarly, I can come up with my distribution for gender, and I can make myself a nice little table here, a very simple table. And I can add across my rows right here. 9 and 21 is 30. 30 and 45 makes 75. I can also do a similar addition here. 56 and 16 is going to be 72, plus 8 is 80. And so it looks like I have males. I've pulled 75 males and 80 females. So what I've done by kind of extracting these two short lists right here, by adding my columns and adding my rows, is I've identified information that sort of strips away the information of one of the variables. Notice that for you to interpret the number 21, you both have to make an interpretation of gender and work status. But for you to describe to me what 29 means to us in this table, that is only relevant to the work status. 29 has nothing to do with gender at all. We've stripped away gender information by adding down the gender columns right there, or adding down the gender rows right there. Very similarly, 75 has nothing to do with work status. 75 is just the descriptor of how many males total. And so in this way, we refer to these as marginal distributions because you write the numbers in the margins of your table. And these help us think about one variable without the context of the other variable, which is typically useful. Finally, a thing that people typically do if they're drawing their marginal distributions is you might as well add these things up and get your total sample size. It's probably going to be relevant. So I'll say down here in the corner that it looks like we sampled a total of 155 people to fill out this table. That's right there. And that's probably just a typical number that we need in computation. So usually when I see this table right here, the first thing I do is I add my rows, add my columns, and you should notice all 6 cells add to 155. These 3 rows right here, or sorry, these 3 columns add to 155, and these 2 rows also add to 155. It should always work out that way. So the marginal distributions are just saying extract just one variable's information rather than have it all mixed as it is in each cell in the table. From this, we can determine simple things. And by the way, let me go add these over here. 29, 101. Oh man, don't start doing weird things to me. Stay there, stay there. 101 and 25 and 75 and 80, and our sample size is the 155. All right, we'll use those guys so I can scroll away here. So first things first, determine the probability that a student does not work. Well, what I can do here is say the not working students. There are 29 total students that don't work out of 155. I think that I could just directly state that right there. I'm not too worried about reducing this down to a percentage. 29 students out of the 155 polled don't work. I've extracted that from a marginal distribution value and the total sample size that we computed. We can determine the probability that a student is male very similarly. By looking at my marginal distributions, I can see that 75 total polled were male out of 155 total. So 75 out of 155. Because this was out of all of the students, we divided by the entirety of the sample size, 155. We can determine the probability that a student does not work full time. And notice here, probability of not full time. I might also notate this as something like full time. I don't know. This is probably bad notation, but I'm putting that apostrophe there to indicate that complement, right? This is the not full time. So this should be the probability that we are not working plus the probability that we are part time. And it looks to me like this is going to be 29 out of 155 plus 101 out of 155. And that should be giving us 130 out of 155. Now, I think the important thing here to do is to realize that we could have done this one actually a little bit smarter. So let's recognize what we can do with this complementary probability. Since it is the case that there is a 100% chance that you either work full time or you don't, I could instead flip this around and say the probability of, and I'll just call this full time like FT right there, just using some different notation here, the complement of full time should be all of the probability that's not associated with being full time there, right? What is the probability that we are full time? Well, that's 25 out of a 155. And it turns out that if we write that 1 as a 155 over 155 and subtract off 25 over 155, then we can go ahead and land there at a 130 over 155, the same thing right there. So doing complementary probabilities as 1 minus not the complements right there is typically a very quick way for us to compute relevant quantities of interest right there. And anytime you see the word not, that usually means you can just flip the problem around, and rather than maybe adding up a bunch of things, you can usually get away with just subtracting off maybe just like one thing. So now we've got a couple more that have the very special word in it. You should notice that our last three examples all say the word given right there, and that's going to mean that we want to be a little bit more careful with computing these probabilities. So determine the probability the student works full time given that they are male. So what this says to me is that we are only computing probabilities out of the males. So the total divided by amounts right now is no longer 155. I know that we're not looking at all 155 people. We are only, in this next problem, looking at the 75 that are males. What is the probability that a student does work full time given that they are a male? Well, out of all of the males, right, there's 75 males, 9 of them work full time right here. And so we are going to get 9 people are males and full time. Divided by, it was given that they were a male. So out of all of the males. So 9 out of 75 right there. This is the same thing as our Bayes rule before. The probability of A given B is the probability of A and B. Okay, so I wrote mine backwards right there. I've got B and A. That is the condition down there. It was given that they were male. So that's what told me to count out of 75. Very similarly, in our next example, it is given. We know that they work full time. So we're counting out of just the full time people. I have 25 total full time people. Those are the ones in consideration here. Given that they work full time, that's the phrasing that tells me that we're going to be dividing by 25 right here. Which ones are we interested in? Well, just the males out of the full-time workers. So it looks like 9 out of the 25 full-timers were males. So here, the big thing to notice is that when you see the word given, it's giving you the restriction. We're not looking at the full sample of 155 anymore. We're just looking at one of the categories associated with that sample. And the last one here, I've just got one other little bonus kind of snag to make us have to think a little bit right here. The first thing that I'm seeing, man, I literally haven't even read the question yet. The first thing that I'm doing is just seeing given that they are female, and that is immediately saying to me, oh, our answer is out of 80. Maybe I'll just, that's sort of my note for this. When I see given that they are female, I know that my answer is something divided by 80. So what's the probability the student doesn't work full time? So it's the probability that they are not full time. So I'll list that as full time complement. given that they are female. And so this should be the probability that they are not full-time, the complement of full-time and female, divided by the probability that they are female. And so notice how I'm going to flip this around again. This complement says to me I should do a 1 minus or something like that here. So full-time and female. I want all the parts out of the females that are not that, right? So here's my full-time females, that's 16 of them. Those are the ones I want to disclude. I'm actually interested in the other ones that are over here. So 56 plus 8 is going to be giving me 64. So it seems like there are 64 females that don't work full-time out of 80 total females. So I'm seeing here 64 total females don't work full-time out of the 80 total females that have been observed that were in this data collection that happened right here. So every time you see this word given in any of these phrases, what they are telling you is what to divide by. All of these what to divide by numbers came from the marginal distribution, which while you probably will not be prompted to create a marginal distribution by listing your values in the rows and the columns as sums, it's always a smart thing to do to get yourself set up for the values that you're going to need to compute there. All right. So every time you see this word given, we're sort of in a sense changing the denominator of our fraction by reducing us from the entire group down to just one of these sort of subgroups, male, female, full-time workers, stuff like that. Okay, I think that's it for my table. I just want to talk about some dice right here. This one should be pretty easy, and I think we'll be able to call it a day right here, right? I think we'll be, let's see. Yeah, I might drag example 4 out till tomorrow. I think I'm going to do that here. Let's just talk about some quick dice things here, a little with replacement, a little without replacement. And we'll do example 4 tomorrow, which will cover our overlapping, non-overlapping probabilities here. Our example 3 here is that we've got a marble bag, 5 red, 4 blue, 2 green marbles here, and we want to talk about some of the probabilities of pulling some of these things. We want to talk about independence versus dependence here is our big thing here. My first question is, what is the probability that we pull a red marble from the bag? Well, this one's really easy. It looks like we have a total of 5 plus 4 is 9 plus 2 is 11 total marbles. So I'm going to say that there are 11 possible pulls that we could get here. It looks like 5 out of the 11 are going to be the red marbles. What is the probability that we pull 2 marbles with replacement and get 2 red marbles? Well, what this means to me is that we need the probability of a red and a red. We are making 2 different pulls, and we want to know their probabilities. Well, when I make my very first pull out of the bag, and I'm going to pull my first red marble, as we just saw, it's going to be a 5 out of 11 probability. But what I need to now do is I'm with replacement, so I'm going to throw that marble back into the bag. I'm replacing it back into the bag, and I'm going to pull a second marble. I now need a second event also to occur. So we're going to multiply a couple probabilities here, and the second probability is also 5 out of 11 because I put that marble back in the bag. That's going to leave me with a 25 out of 121 for my probability there, just by multiplying across on the top, multiplying across on the bottom. Again, we could get a decimal or a percentage right there. I'm not super worried about that for right now. As long as we can get our fraction, I'll be happy. What we want to see is how is this different if we did not put that marble back in the bag, right? So I still have this red. Oh my gosh, I can't get my P's and my R's distinct from each other right here. This probability of red and red. I don't really know that there's a common way to denote this with or without replacement in these probability statements here, but we know that it's in this sentence. So the point now is that after I pull my first red marble, which has a 5 in 11 chance of happening, my probabilities are now different because now I didn't put that red marble back in the bag, right? So now I should notice that since I didn't put that marble back in the bag, only 10 of the remaining marbles are in there. Or sorry, only 10 of the marbles are remaining. One of the ones is the red one that I removed. There used to be 5 red, but I pulled one and it's no longer there. So now it's that only 4 out of 10 of the marbles remaining are going to be red. It looks like that's going to leave us with a 20 out of 110 probability right there, or that I certainly see it that simply reduces to 2 out of 11 right there if we wanted to reduce that guy. But notice here this difference in this first example or the first kind of real example right here, these events were independent of each other. The second probabilities had no influence from the first probabilities right here. On the other hand, in the second one, the probability of our second event was fully dependent on what happened in the first event. The fact that a red marble got pulled and didn't get put back in the bag influenced what our incoming probabilities were for the next event. So in these two that are very, very similar here, I would compare them by saying this example here with replacement makes these events independent of each other, because when we put the marble back in the bag, all the probabilities for the second draw are the same as the probabilities as for the first. When we don't put the marble back in the bag without replacement, now the probability for our second draw is different because of what happened in the first draw. Therefore, the second marble's probabilities are dependent. They depend upon what happened in the first. So these are dependent events. So it's super typical to talk about marbles and with and without replacement for the distinction between independent and dependent. And we see that when two events are independent, the probabilities don't change from one trial to another. When two events are dependent on one another, the probabilities do change from trial to trial to trial. So let's go ahead and calculate just a couple other quick ones right here, and we'll go ahead and call it a day for today and do the rest of these tomorrow. What's the probability that we pull 3 marbles with no replacement and we get a red and then a green and then a blue? So I know, so I'm going to do probability red, then green, then blue. So my first marble, I'm going to pull the red. I know that 5 out of 11 of the marbles are going to be red in the bag. But now I'm not putting them back in, right? So now what I know I have, and maybe what I should notate here is just like kind of where I'm at so far. I've got my, nope, yep, red, green, blue. I'm starting with 5, 4, and 2 there, right? But what's happened now is I've already dropped myself down, so I've actually only got 4 reds that are left over right now. The next thing I want to do is I want to draw a green. I know that there's 4 greens in the bag according to my notes, but that's only out of 10 total marbles now. Wait. Oh yeah, there are 4 out of 10 are going to be green right there. And then I would like to draw a blue. And now that I've drawn the green, I know that there's only 3 greens left in the bag. Now I'd like to draw a blue, and I know that there's 2 blues in the bag, but I can see now that there's actually only 9 marbles collectively in my bag right there. So it looks like in total, 5 times 4 is 20, times 2 is 40. On the denominator down here, 90 times 11 is going to be 990. If I want to slightly simplify that to 4 out of 99, I think I could state that as my probability there. And again, since we weren't putting them back in the bag, we're seeing the number of overall marbles dropping with each pull that we're experiencing right there. Yeah, exactly. The denominator drops by 1 each time right there. And finally, we can look at one that's got a little bit of this sense of complementariness right here. What's the probability that we pull 2 marbles with replacement and don't get any green? So we are going to put them back. So probability of 2 not greens means the probability of red or blue and red or blue. So I could rewrite this as so, feel free to like give yourself some notation for some of these things here, right? And using words like and or are really going to be our friends here. So for our probability of red or blue, I can see that out of the reds or the blues, it's going to be 6 out of the 11 marbles are red or blue. 5 of, oh wait, that's a lie. 7 of our marbles, I'm looking at my crossed out numbers right there. 7 out of our 11 marbles start out as red or blue. It's 4 of them that start out green. So 7 out of 11 for red or blue. And I would like to draw one, put it back, and then draw a second. And so you should see here also that when we have these independent events that we're doing repeatedly, it looks like we can actually just list a fraction to a power here. In this case, 49 out of 121. I know that's not going to reduce because that wasn't going to reduce and we didn't introduce any new factors by squaring it. So it looks like that would be our simplest possible final answer right there. 121 right there, 49 out of 121 for these guys. So Independent versus dependent is getting handled very often in examples as this with replacement, without replacement. We always want to ask ourselves, if we were to do this trial a second time, would our results depend on what happened the first time? Our ones that we're going to pick up with tomorrow is going to be our overlapping or non-overlapping. Hearts and clubs in a deck of cards do not overlap, but hearts and queens do have some overlap. Those are events where there could be the same thing getting picked for both groupings there. So we'll pick up with this tomorrow and then head off into 3-3 and 3-4. I think the only other thing I want to say about these ones right here is just that when we're talking about independence versus dependence, in a lot of cases, it's set up to be explicitly known whether we're going to be independent or dependent. But in a lot of cases, there's like literally science that is done just to determine if events are independent or not. I think one of the really good examples that people very often talk about is, for example, in sports, things like shooting multiple free throws in a row, things like being a kicker on a football team and kicking field goals. It's been pretty widely shown that if you miss your first field goal in a game, that your probability of missing on your second one is much larger. Whereas if you are successful on your first kicking of a field goal, you are more likely to make your second. Very similarly, free throws can have a lot of pressure. If you make your first one and you know that you really need to make the second one, there are some players in the NBA who they are truly independent events, and you can see that their second free throws have the same probability of success whether or not they made their first. Other players in the NBA, you can see statistically, when they make their first, it becomes a reduction in probability that they make their second or an increase or vice versa. So independence of repeated trials in sports is actually a really interesting thing to study because it's not the same across all sports. It's not across the same. It's not the same across all players within that sport. And as you can imagine, a lot of sports, there's a lot of things that are like, just because you've shot like literally 100,000 free throws in your life, pressure is different. Home field versus away is different. Is this the game-winning shots, or are we still in the second quarter? A lot of these things actually make a difference, and so studying whether or not two events are independent is sometimes the actual subject of the experiment itself, rather than just one piece of information required to compute some associated probabilities with some things. And so. So there's my wrap up for things right there. So let me at least briefly talk over here to the answers in some of the chat over here. I got to run along to my next lecture here. But if you're looking to go into an undergrad degree in pure math next year, that's exciting. That I have my master's is in pure math rather than applied math, which was for me was actually probably not quite the right direction to go right there. I am more of an applied math kind of guy. But I really do appreciate the proofwriting side of things. So what I would suggest is that if you're going into pure math stuff, some of the nice thing to see is that there are lots of, in a sense, like alternate textbooks for lots of more applied type math things. So for example, you can find some calculus textbooks that are intended for first and second year calculus students, but they have a much more heavier emphasis on the proof of why some of those things are done. Some of the names of these are escaping me right now. But lots of schools have classes that are referred to as typically advanced calculus or introduction to proofs. And in a lot of those classes, you'll kind of go back and work through your introductory proofwriting stuff that's associated with that. Linear algebra is very often students' first proofwriting course. Yes, Apostle and Spivak are, I think, the two names that I was looking at right there. I've heard of a lot of people talk about Spivak. I've heard about the Apostle one a little bit more recently. I know that Apostle actually teaches Calc 1 completely flipped. Typically, you do derivatives first, then integrals. He does integrals first, then derivatives because it's a lot easier to prove that his results are correct when you do it in that alternate order way. And so those, I think, are the two books that are very rarely used as first introduction to calculus books, but that's because most students aren't looking to go into pure math. So I do think that those are the, in a sense, better approaches if your goal is to, rather than be an engineer, be more of like a math major that goes to get that next degree that's out there. Because I think that it will help you see those topics for more what they really are, rather than as being computational topics, as being things where it's like that's a really weird claim. All the claims that you're making have to do with infinity. We need to define a good system where we can actually, in a sense, prove that those things are legit rather than just being like, that seems right. And there's a lot of hand waving that happens in a lot of early calculus stuff that's nice to not do if you can actually just be formally right. So if those are the books that you're thinking about, then I would say you're headed in the right direction with your thoughts right there. And my other thing to just say is that as you're exploring the things that you're doing, I'd say keep an open mind about pure versus applied things. I think that linear algebra is the best undergraduate example of if you're going to be an applied mathematician, linear algebra might be the most important class that you take. And if you're going to be a pure mathematician, linear algebra might actually be the most important course that you're going to take. It's the one that splits the difference the most between pure and applied applications. So I also think that on the extreme other end of things, if you're going to be a very applied mathematician, then computer science combined with linear algebra is really the most powerful combination. But again, pure math, so much of the nicest parts about a lot of proofwriting is handling things collectively by proving things as matrices and as vectors rather than dealing with standalone quantities. So linear algebra is really, in my mind, one of the most important ones because it is one of the most important pure topics and it's one of the most important applied topics. So I would say don't pick too soon about whether you think you're a pure or applied person. Wait on the picking on that and take the classes that are related to both early, like you're talking about with your calculus textbooks, and then with some linear algebra because those always are going to combine with both topics that are out there. So, and I'm going to say to every person ever that I think is interested in math, I'm going to say to every person that's interested in pursuing a degree in math, what I wish was told to me, which is that you should learn to program because there are not a lot of mathematicians that get paid to do math without writing code these days. Um, it's it's 2020. Learning to code is the relevant application of being a mathematician. Even if you're a pure math person, being code competent is going to be your friend. So always think about dabbling in some computer science stuff, always. And honestly, I think that even if you're just interested in the pure theoretical ends of some math things, in my opinion, some of the most interesting pure math that I've seen is proving results in computer science. And so I think even if you're still interested in the pure end of things, always be thinking about CS. I think it's the most interesting, both applications in industry as well as the most interesting theoretical academic applications of math. A lot of stuff in computer science there. So stay broad with your search. Don't try and focus too soon. You can really develop a focus in like grad school. Exploration and making sure that you know what you want to study, I think, is what our undergrad is for. So it's good that you're already thinking about a math degree there, and think about programming, think about the distinctions between pure and applied, and have a little finger in all of them so that you know for sure what you're doing. Because, like I said, I sort of accidentally got my master's in pure math when at heart, I'm an applied mathematician. I wish somebody would have nudged me in a slightly different direction. Hasn't really impacted what I do now, but like still, it wasn't even a distinction that occurred to me to think about. And so the fact that you're thinking about that is good. So yeah, so I'm going to wrap this up here now. I'm going to do a Calc 2 lecture here in 45 minutes. Thank you guys for being here today and for those good questions there. I am going to pick back up. Technically speaking, my last example right here is the last part of section 3.2. So I'll pick up with this tomorrow and then we'll look at our 3.3 and 3.4 topics, some contingency tables, other stuff like that. We'll pick those up in tomorrow's video. Happy Monday, week 4 of everybody. And I will see you guys tomorrow for Tuesday's lecture here. See you guys then.